Hey guys, it's notes number 10. We're going to be exploring area between curves again, but from a different perspective, okay? So notice how we're still finding the area between the curves, right? But now it's going to be a relation in terms of y. And the whole idea of this word relation, it's really an equation still, but you can't call it a function because these equations are graphs, but they don't pass that vertical line test. They're not considered functions, okay? But that's just a minor part. What you also want to know, big takeaway before you leave, is understand the pros and cons of integrating with respect to x or with respect to y. Like what the heck is the difference, right? So keep that in mind. As always, make sure that you guys have your calculator ready just to make sure we're all on the same page. Make sure you guys reset it. Second plus 712 to reset. Okay, so here we go. So remember that when you had a graph with two functions, okay, to find the area between, so in this case, I was never good at coloring in between the lines. To find the area of that region, all you guys had to do was to integrate the top function minus the bottom function. Because if you were standing anywhere in the middle and you were to walk upwards, you would clearly hit the top function. In this case, it's f, okay? And if you were to stand anywhere and you walk downwards, you would clearly hit that blue function g of x. So this here is just the integral from a to b of f of x minus g of x, also known as top minus bottom. It's not always going to be f and g in that direction, okay? So here are some other scenarios, okay? So what's happening here is, remember that before you guys were finding the true area under the curve, we had to approximate. So what happened here was that you guys had a bunch of rectangles, okay? I'm not going to draw all of them, but notice how all of those rectangles are varying in height. Okay, so if you were to technically, theoretically, throw in an infinite amount of rectangles, you'll get that green shaded region, right? But notice the orientation of this rectangle. This is a vertical rectangle. Okay, now a vertical rectangle has a width that's horizontal. We call that delta x. Okay, now when delta x, when we squeeze in an infinite amount of rectangles, that delta x gets smaller and smaller and smaller and closer to zero. So what's happening is, when you increase the number of rectangles, delta x gets closer to zero. The width gets really skinny, right? So when you go arbitrarily close to zero, that delta x is represented by this dx right here. That dx isn't really just like a symbol. That represents that your horizontal width is getting closer to zero. And this right here is really just your height. So again, it's really just your width, which is your base, and your height. So you're just finding the area of an infinite amount of rectangles at a very fast rate. That's what integration does, right? So how would it work if, let's say you had something that looks like this, okay? So the shaded region, I'll roughly color it in. And you guys can just roughly sketch this one here. The issue with this is, if you stand anywhere in that region, okay, what is your top and bottom? Excuse me. Okay, so here's the issue with that. If I stand right here and I walk upwards, it's green. But if I stand right here and I walk upwards, it's purple. So which one is it, right? So notice how there is no clear top and bottom. So what you do is you resort to maybe changing your perspective so that you can integrate a little bit faster. If you notice, if you stand anywhere and you walk towards the right, it's clearly purple no matter where you stand. If I were to stand here and walk to the right, it's still purple. If I walk over here to the right, it's still purple. There's a clear right function, okay? And similarly, if I stand anywhere and I walk to the left, it will always be that green function. So there's a clear right and left function here. So what we're going to do is we're actually going to instead shift our perspective and think of horizontal rectangles. So we're still finding the area the same way, okay? But now what's happening here is the width of that rectangle is really delta. Notice how that's going up and down right here, right? So that's really delta y, the change in your y values, okay? And your height is really determined by your right function minus your left function. So here's what I'm getting at. When you have horizontal rectangles, you will always integrate with respect to y, okay? Your delta y is really your dy, and your right minus left really gives you your height. So same idea, just a different perspective. So something that you may be asking right now, well, why do we need to get fancy with it, right? Why do we need to integrate with a different variable? So I'll show you throughout the lesson why it's sometimes necessary, okay? So pretty easy to remember. If you have vertical rectangles, you're doing top minus bottom. Vertical rectangles just means x, okay? So I want you guys to equate these two. Vertical rectangles, think of x, because that's going to help you guys out later, okay? Now, if you have horizontal rectangles, that implies that you're integrating with y, which is right minus left. Pretty easy to remember, okay? Notice how the bounds are also in terms of y here, okay? Whereas the other one, everything was in terms of x. Okay? Probably a lot easier if I show you an example. So here we go. So go ahead and write this down. Example 1. Find the area of the region bounded by the graphs of x equals 3 minus y squared and x equals y plus 1. Okay, so first things first, a telltale sign that you have to integrate with y is if your equations are not in terms of x. So usually we're so used to having y equals x squared plus 4x plus 3. Everything was in terms of x here, and y was by itself. But if you notice equations where y is not isolated, notice how y is not by itself here or here, right? That's a telltale sign that we're going to integrate with y, all right? So how do you know when to use which? To answer the question to that is take a look at your equations. If it's in terms of x, keep it at x. If it's in terms of y, keep it at y. All right? There are some exceptions, but we'll get to that later. Okay, so just like the previous problems in the last section, the first thing you want to do is get a picture, right? Now, although you're not expected to graph relations by hand, it's important that you guys understand where things come from, okay? So let me just give you guys a quick sketch here. And you guys can graph along with me. This is just a rough estimate of what this looks like, okay? So take a look at this equation right here. X equals 3 minus y squared, okay? Just to make this a little bit visually easier, I'm going to go ahead and put the 3 at the end, okay? Now, the only thing different here is that your variable is different, right? The y is being squared. So I want you guys to think, when you usually have a square, what shape do you guys get? Okay? So when it's usually this, y equals x squared, you would have a parabola that's up, right? Okay? Now, what if you had a negative x squared? That parabola would be reflected down, right? So it's the same idea. What do you guys think happens if you have x equals y squared? Okay, well, actually, x equals y squared is still a parabola, but it opens up towards the right. Okay, so what do you guys think happens if it's a negative y squared? That's really just a parabola that opens up to the left. Okay, so I want you guys to at least understand where the picture that I'm about to show you, how they got it, okay? Now, if I put a plus 3 here, what does that do, right? So remember, that's your k. So it would just take your parabola and shift it upwards 3 units, okay? So what do you guys think happens in the opposite world, right? Plus 3 here would actually move it towards the right, okay? So in the x realm, it's things that are facing up and things that are facing down. In the y world, it's things that are facing to the right and to the left. So we're moving in opposite directions, really. So x equals negative y squared is a parabola that faces to the left that moves 3 units to the right. So I want you guys to understand where they got this picture from. Okay, so it's something like that. X equals negative y squared plus 3. All right? Now, this second equation, okay, what should that look like? Press play when you're ready. That should definitely look like something linear, okay? So if I just maneuver this, because linear functions are so easy to graph, if it's x equals y plus 1, then y is equal to x minus 1. So if you guys remember back in Algebra 1 or Integrated Math 1 or maybe even middle school, right? You plot your y-intercept, which is negative 1, and then you rise and you run 1, and you graph your line. Boom. Something like that. Okay? So notice how there's a region that's bounded. Okay? It's this nice shape here. Okay? So a picture gives you two things. So remember in the last lesson, a picture gives you two things. What information does it give you in regards to the area, okay? Pause, really think about that. What does a picture tell you? Or what information can you get from a picture? Okay, so remember, a picture does two things. It tells you what your top, bottom, left, or right functions are, okay? So top, bottom, left, or right. But then it also tells you where the intersections are. Or at least you can find it, all right? So clearly that purple function is the right function because I'm walking towards the right, I will always hit a purple no matter what, right? And if I'm walking towards the left in that region, I will always hit that blue line. So if I'm integrating with y, I'm just going to draw a sample rectangle there just to remind myself that this is dy. Horizontal rectangles tell me that I'm going to integrate with y. So let's write down what we know. We know it's going to be with respect to y. It'll be right minus left. So I'll just write it up here, right minus left. My right function is negative y squared plus 3, or the original 3 minus y squared. I'll leave that up to you guys. I'm going to write the original. Minus the left function in terms of y is y plus 1. Notice how I didn't use the equations in terms of x, right? So everything here is in terms of y, but that means that the bounds also need to be in terms of y. So how do you do that, right? The issue with this is it's kind of tricky doing it on a calculator, all right? So what you do, when they intersect, they are equal, okay? And this is just a little bit of algebra, so I'm going to go through this pretty quickly because I don't want you to think that that's the overall lesson of this, overall part of this lesson. So here we go. So what we're going to do is we're going to take our two equations, so 3 minus y squared, and we're going to set it equal to y plus 1. Because you set them equal to each other to find your intersection. Okay? That's basically what your calculator did in the last lesson, right? Okay, so if I maneuver this around, if I move the y squared over and the 3, I would get positive y squared plus a y minus a 2. Okay, and I'll quickly write that in so you can see. Okay, this allows me to factor. That's just y plus 2, y minus 1. So that tells me that y is equal to negative 2 and 1. The question here is, what the heck does this mean? Okay, those are your bounds, you guys. When you set your equations equal to each other and you solve for it, that is where they intersect. So here they intersect in terms of y from negative 2 to 1. Sometimes you got to do things by hand. Okay? Okay. So once you have your integral set up, the rest is easy. Okay? We can do this by hand, but for the sake of time, let's just do it with a calculator, okay? So what you guys are going to do is you're going to type this out. Now, it's different because your calculator is both smart and dumb at the same time. It can do so many things, but there are restrictions to it. For instance, it can only graph functions. It can't graph relations, right? So here, when you calculate on the home screen, what you're going to do is you're going to press Math 9 for your integral. Negative 2 to 1. Make sure you don't use the minus sign. Use the negative sign, okay? Okay, even though this says y here, you're not going to type in y. What you're actually going to do is you're going to type in 3, parentheses 3, minus x squared, minus parentheses x plus 1, close with respect to x. Okay, so all we did was we switched our variables, so the calculations should be the same, okay? But you can only do that after you set it up. Go ahead and plug and chug there. I'm going to try to do that faster than you, but I'm on the computer, so this is going to take a little bit of time. Okay, so once again, it's Math 9 for the integral symbol. From negative 2 to 1. We're going to have 3 minus x squared. Now, before I continue, some of you may get caught up with these parentheses. If you're having trouble keeping track what you can do is you could simplify the inside first before you calculate. So for instance, I could have just changed this to 3 minus x squared minus x minus 1 if I distribute that negative. And then that's a lot easier to type. I could even simplify it some more and just call it negative x squared minus x plus 2. Okay? That's if you have trouble keeping track of your parentheses. But if you have no issues with that, then forget what I just said. Okay? But I will tell you guys that 90% of the time, people set it up right, but they get it incorrectly just because of a syntax error. Okay? So just keep that in mind. Okay, 3 minus x squared with respect to x. And you guys should get 4.5. Okay? All right, so remember, big takeaway. If your equations are in terms of y, that's probably telling you to integrate with y. Almost always, okay? That implies that you have a horizontal rectangle. So remember, horizontal rectangle, dy. All right? To find your intersections, you have to set your equations equal to each other. Sometimes you have to do that by hand, okay? But if you have assistance with a calculator, you could always use that intersection piece. The reason why we didn't do it here is because we weren't able to graph relations, okay? We can only graph functions. So it has to pass a vertical line test. Okay, so could I have integrated in terms of x, right? So if you notice here, here's the big issue. This is the picture that we had, but not as good looking as mine, right? If I stood here and I walked upwards, that hits the line. But notice how if I stood over here and I walked up, it was the parabola. Okay? So right at this pink line, the top functions changed. Okay? Now, if I stood here and I walked down, it's still that parabola. And if I walk down here, it's still that parabola, right? So technically you could find the area, but then you would have to set up two different integrals. And I'm not going to bore you guys with it, but basically this is what you would have to do if you were really insistent on using delta x or dx here, okay? So notice how with dy here, in this case, it was a lot faster and efficient, right? So just keep that in mind. We could have chopped it up into pieces, but then that requires a lot of work on our end, okay? So here's some for you guys to try. Let's call this part B. Okay, so this one is a little bit tricky because this equation is in terms of x and y is by itself, right? But this one isn't. Notice how the y is not by itself, okay? So what that tells me right away is that I'm going to integrate with y. That just makes things a lot easier, okay? So what we have to do here is we got to make sure that our equations are in terms of y, right? So I'm going to solve for x here. X will equal y plus the 1 if I move that minus 1 over. And over here, if I'm trying to get x by itself, that's going to be y squared minus 6. And then if I divide the 2, that's going to be y squared over 2 minus 3. Okay? Anyways, here we go. Here's a rough sketch. Really, you're sketching it so that you can figure out what the right and left function is here, okay? So although this, well, you know what? Let's graph this first. Y equals x minus 1 has a y-intercept of negative 1, and it rises 1 and runs 1. So we got something that kind of looks like this. It's an increasing linear function. All right. Okay, over here, although that's not as clean as we want, you guys should know what that should look like. Okay, so that's definitely a parabola. And that minus 3 is, it's moving towards the left. Okay, let me double check because my picture is off. Wait a second. Oh, okay. So y squared, since it's positive, I know it's opening up towards the right. Okay? That negative 3 just means that I move it to the left 3 units. The reason why I'm kind of rushing that is because you're not going to be required to sketching this. But I do want you guys to get at least a small understanding of how they got the picture. Okay? So, all right, here's your region. Go ahead and pause if you'd like to do this on your own. And press play whenever you're done or if you need some guidance. Okay? Okay, here we go. So we're going to set up our integral. I know this is going to be with respect to y because there's a clear right function and a clear left function. So I should say equation or relation. So my right equation is the linear function. So I'm going to write y plus 1. Remember, it has to be in terms of y. So you can't write x minus 1 here. Okay? Okay, so that's my right function minus my left, I keep saying function, equation or relation. My left equation will be y squared over 2 minus 3. Okay, what am I missing here? All I'm missing are my bounds. Okay, how do we find our bounds? Remember, to find out where the bounds start and stop, that's pretty much where they intersect. Okay, so we're trying to look at where these rectangles, these horizontal rectangles, are starting and stopping, right? And they happen right at the intersection point. So we're going to go ahead and set these two equations equal to each other. So y plus 1 will equal y squared over 2 minus 3. I need a little bit more space. And again, I would say that this is probably more detailed than the AP exam. So the AP exam is a little bit more straightforward. But here we go. I'm not a big fan of fractions, so I'm going to go ahead and multiply everything by 2 just to get rid of that denominator. Okay, so that's going to be 2y plus 2 is equal to y squared minus 6. I have a quadratic term, so I'm going to move everything away so that one side is 0. So if I subtract the 2y over, and if I subtract the 2, the left side would be 0. I'm going to get y squared minus 2y minus 8. Okay? All right, so that comes out to y minus 4 and y plus 2. So that tells me, using the zero product property, y will equal a positive 4 and a negative 2. Okay? What does that mean? Positive 4 and negative 2 is where the region starts and stops. Okay? So negative 2, positive 4. Now, this is pretty much enough for you guys to type it in. I would probably, personally, I would clean up the inside. Okay, I would just have y plus 1, distribute this negative here, and divide it by 2, I'll just put 1/2 or 0.5 just to make my calculations a little bit easier. dy. And that's easy enough for me to want to type it out on a calculator, okay? So here we go, Math 9. And if I'm going a little bit fast, feel free to replay, okay? And feel free to text me if you have questions. So we have y plus 1. So in this case, we're just going to type x plus 1 minus 0.5 x squared plus the 3 with respect to x. So if you did it right, you should get 18. No worries if you did not get 18, okay? Most likely, we just need to figure out what the error was. It's probably a negative or a minus symbol or a parentheses. If you feel like you can type this entire integral up here by itself, then go ahead and do that, okay? I just find that when people see a lot of parentheses, they tend to lose track. All right? And there you have it. Okay? On to the slightly easier ones. Okay? Here's part C. So we actually did the tough problems first. Most of the time, they're going to give you a picture on the AP exam. Okay? Now, let's assume that we don't have that right there, so I'm going to cover that up. Okay? But this is what they would give you. All right? Is this what I had? That was... Oh, yeah, okay. So, not this one. This is the one we just did. Dork. Okay, here we go. Go ahead and try this one, part C. Press play when you're ready. Okay. Probably 95% of the time, they will give you the picture and all of the details. Okay. So here, it's obvious that this will not be a top minus bottom because there's no clear top function. Okay. So this is probably telling me to go horizontally in terms of y, but I also noticed that the equations are looking a little bit funky, right? Everything is in terms of y, so that's a good telltale sign that I'm integrating with y. Okay, so here we go. We know that we integrate with y. It's clear that when I stand in the region, the right function, the right equation is that pink one, which is x equals 2y minus y squared. So that'll be 2y minus y squared minus the left function is clearly that, I keep saying function, the left equation is that blue one there, which is y squared minus 4y. Okay? They actually give you the bounds, but remember, your bounds are in terms of y, okay? So pause here, think about what your bounds should be. Okay, so your region starts here, and it accumulates a bunch of horizontal rectangles, right? It moves all the way up until it stops right at the intersection point. At what y values does that region start and stop? It starts at 0 and it ends at 3. We would not be using -3 because that is the x coordinate. So we went from 0 all the way to 3. Okay? And then you plug in chug. I'm actually going to skip that part. I'll let you guys deal with that. All right? Here's the last one for the day, part D. Go ahead and try this one on your own. Press play when you're ready. Okay? Just by looking at the equations and knowing that there's a clear right and left instead of a top and bottom, I know I have to integrate with y. Okay? Clearly, the right function will be the square root of y minus the left function, which is y squared minus 1. Make sure that you guys are using parentheses when there's more than one term, okay? Okay, so remember, dy means you're drawing a bunch of horizontal rectangles. So you're accumulating, starting here, moving all the way up to the top. So at what y value does the region start and stop? So notice how it starts at a y value of 0. And it works its way up all the way to a y value of 1. So those are your bounds. Okay? That's probably the toughest part, figuring out your bounds. Okay? And then the rest, You guys can type out. I would definitely distribute if you're not comfortable with the parentheses. So yeah, practice your calculations, practice setting it up. I just want to encourage you guys, the most important part is the setup. If you can get the setup down, you have the hard part done. Okay? Now, if you have a calculational error, that's something that we can easily fix. But your main focus, you guys, is on setting up the integral. What's the first function, what's the second function, and what are the bounds? Okay? So you have a few problems in your PDF. It's not on Delta Math here, okay? So go to Canvas, go to Homework 10, and go ahead and check that out.